This is Professor Iris Miano here with a lecture video on section 7.1 and 7.2. Now this is the first lecture video concerning content for Unit 4. Even though you're watching this right before you're going to take your Exam 3, just note that this information is not a part of Exam 3 material. Okay, so what is the beginning of Chapter 7 all about? Well, this is when we're going to get into graphing, linear equations. In fact, we'll just leave it at that for now. And before we have our, probably for most of you, reintroduction into graphing linear equations, let's have a short review on what the Cartesian plane is. So as you can see from the figure down below here, it is a two-dimensional grid, which is the intersection of the x and the y axis. The x-axis is always this horizontal line right here. It always has a horizontal configuration to it, whereas the y-axis is always the vertical axis. And you can use this coordinate plane, or Cartesian plane, I guess as we're calling it. It has a couple of different names to it: xy plane, Cartesian plane, coordinate plane. Yeah, so those are the ones that I know off the top of my head. But you can use it in order to plot ordered pairs, which is how we represent points. You can graph lines, curves, lots of different things. So what kind of things do we want to write down for our bulleted points in defining a Cartesian plane? Well, let's see. Let me get my drawer ready, and I want to pick this color right here. Oops, just a sec. Get out of there. Okay. It is a two-dimensional space. It is the intersection of an x-axis, let me rewrite that again. Handwriting's getting a little terrible here. X-axis and y-axis. And you can use it to plot points, lines, curves. Looks like an E. Curves, etc. Okay, so here's your x-axis, the horizontal. Here's your y-axis. Here is an example of plotting a point. And in this case, the ordered pair would be 3, 3. Just as an example, here is an example of plotting some line, right? That's a line. And if you wanted to plot some curve, you could do so. And generally, whether you're plotting lines or curves, usually the beginning and the end of the trajectory has arrow points associated with them, but not always. We're going to be sticking to lines and points mainly with our discussions in these sections. So if you are talking about the equation of a line, which is, this little bit right here, you will have two variables associated with it, x and y. And in order to find a solution to a linear equation, you need to find the values that satisfy all of the variables of that equation. Okay, so we're going to be defining a solution to an equation in terms of linear equations of two variables. So it is xy, x comma y, can be a solution to an equation. And we'll give a general form for the equation. Ax plus by equals c. We'll give what we call the standard form of the equation of a line and two variables if it satisfies the equation. Now, what does it mean to satisfy the equation? Well, that just means that when you plug in these values x and y, and then you simplify both sides of the equation, it simplifies to the exact same value on either side of the equal sign. So we'll practice this in this very first example here. We're going to use this equation, which is in standard form, where a is 3, b is -2, and c is 8. So we want to know, do the ordered pairs -1, 3 or 0, -4, are either of them solutions? So here's how you'll address the first one. Just go ahead and take your equation, and every time you see an x, plug in a -1 instead. So that'll look like 3 times -1 minus, 2 times, what's your y value? It's a 3. So instead of a y, put in a 3. And does that equal 8? Well, that's what we're going to try and find out here. So upon simplifying the left-hand side of the equation, we essentially want to see if it equals 8. And if it does, then we'll say that -1, 3 satisfies the equation. Let's go ahead and see. So let me get some more fun colors going on here. So I'm going to perform the multiplications on both of those terms in order to figure out what they settle down to. So this will be -3 minus 6. Is that equal to 8? Well, no, because -3 minus 6, if you want, you can do a little kind of a addition of the opposite thing to deal with that algebraically. If you have questions on that, I can elaborate more. But for now, we can just go ahead and determine that no, this is not equal to each other. So therefore, we say it's not a solution. So -1, 3 is not a solution. To this equation, or just say it's not a solution and leave it at that. That's fine. Now let's go ahead and try this other one, 0, -4. So instead of an x, for this, again, the same equation, put in a 0. And instead of a y, put in a -4. This is looking promising. But yeah, essentially we're like, are they equal? I don't know. Now notice what's happening here. With this first term, this 3 is being multiplied by a 0, so it zeroes out. Oh, hold on. I want to go back to draw. So that's a 0, right? It's like gone. So we're left with -2 times -4, and that gives us +8. And that matches the +8 that was already on the right side, so yep, that's good to go. Indeed. Wow, this editor that I used to do the drawing on top of my notes, it got updated, and I don't like the new update. It's clunkier to work with, but oh well. I'll have to find another thing to work with if I have time in the future. In any event here, this ordered pair of 0, -4, when plugged into the equation, settle down to something equal on both sides of the equation. So that means that whatever I plugged in, this ordered pair in this case, it satisfied the equation. So we say, so therefore 0, -4 is a solution. And let's go ahead and box those up. Sure. Let's get some closure to that. Cool. Great, moving on. Now we're going to get into some graphing methods. And here is the first one, table of values. So the idea is you create an XY table. That doesn't necessarily look like an X. Let's try that one more time. Picking appropriate values for X. Now, how do you know which values are appropriate? Well, there's some standard ones that you can try first, and if you find that the ones that you've tried are not appropriate for whatever reason, it's just not within the window of the Cartesian plane that you have, or you deem it inappropriate for other reasons, then you just pick different numbers. Literally, whatever is chosen for your X values is, it's in the eye of the beholder. You can choose whatever you want. I recommend that you try and make them appropriate though, and I'll give you some pointers on what I think that is as we go. Appropriate values for X and calculating Y. Calculating the corresponding Y values. And then you graph the points and connect the dots. That's all there is to it. It's supposed to be two ends. Connect the dots. Okay, so here, let's make an XY table. Okay, and it's probably a good rule of thumb to have 3 points, but technically for a linear equation, the minimum number of points that you need to graph in order to draw the line is 2. But I think it's nice to just be on either side of a 0 input. So I would go a -1, a 0. My bad. The next consecutive number after -1 is 0. Duh. Okay, go back to the draw here and there and see what you get. Oops, that's supposed to be a positive 1. Let me just erase this bit. Great. -1, 0, and 1. These are the 3 values for X that I have chosen to calculate my Y values for. So basically, it's just, and the more you get into this, the less work you might have to show here, but it's like just plug in a -1 for X and then solve for Y, and you will get Y equals what in this case? Well, Y has to equal 4, right? Because that's the only value that when you add -1 to it, you're going to get a 3. So Y equals 4 in this case. All right. And if you plugged in a 0, Y plus 0 equals 3. Well, that's gone. So it's just Y equals 3. And then Y being a 1, what do you have to add X equaling 1, what do you have to add to that 1 in order to get a 3? In that case, Y will equal 2. So your ordered pairs are -1, 4, 0, 3, and 1, 2. So you'll plot those on your coordinate plane here. -1, 4 is right there. -1, 4. And I'm just labeling them for the sake of, completeness here. Here's 0, 3. It's also called the y-intercept, 0, 3. And then here is 1, 2. And notice that all 3 of these points lie on a very clearly defined line, right? That's good. That's what you should expect. And if you have your ordered pairs that you calculated over here with this XY table wildly deviating from, forming a line, then something's up. Something went wrong. And you'll want to look in your calculations for any errors, okay? So now I'm actually using a straight edge on my screen there. It is a little bit wobbly, but you guys get the picture. When you're doing this kind of stuff in homework, you're going to be using the graphing utility within the online homework, so you will be creating beautiful straight lines when you work on this stuff, okay? So yeah, there you go. There's the plotting points method, or table of values, which leads to plotting points, okay? Yeah, so I don't know. This method has a couple of different names, obviously. I just called it the plotting points method. This lecture notes calls it table of values. The table of values allows you to get points that you know have to be on the line, you plot them, and then you connect them with a straight trajectory with arrow points, making a line. Okay, great. Moving on. Okay, so let's use the same table of values method in order to plot this other line right here. And just to mix it up, I'm going to choose a different color. Let's go this teal color. Okay, so again, come up with an XY table. And be very careful with what you choose for your input values for x here, because the only thing you're going to do to manipulate that x in order to turn it into a y is multiply it by 1/4. Now, whenever you're tasked with doing this, I recommend that you choose input values for x that are going to cancel out that 4 in the denominator straight away. So a 0 will do that because it's just going to, anything multiplied by 0 becomes a 0. So definitely have a 0 in there. I'll kind of put that in the middle of the space provided. And then I would choose a negative number and a positive number that will cancel out with the 4. So think about having a 4 or negative 4 in the numerator space of the x, right? Which is to say, I would choose as input values for x around the 0 as -4 and 4. Okay? So again, the -1, 0, 1 is like the standard go-to, like start jumping off point for input values for x when you're using this table of values method, but that's not necessarily what you always want to pick. That might not always be the best choice, because you don't want to have to plot, a fraction for either your x or your y value when you're plotting points in the Cartesian plane, right? You want to plot integer values, things that are representative by these intersections of these blue lines that make the corners of the grid, right? So yeah, be kind to yourself and choose values that are going to cancel when you have fraction multipliers. So here, notice that the 4's cancel, it's still very much negative, so that means y in this case will be a -1. 0, right, we'll just, 0 out this whole thing, will equal 0. And then here, you'll have 1/4 times 4, which the 4's will cancel, and you'll just be left with a 1. Okay, so the ordered pairs that we're going to plot here are -4, -1, 0, 0, and 4, 1. Okay, so here's a -4, -1 right there. -4, -1, all in between. Here's 0, 0. And here is 4, 1. And then check that out. They totally lie on a line. What line? Well, approximately this line. Okay, that looks pretty good. I like it. Great. So there are more methods, and here we go, trying to outline them. Let's first, before we introduce another method, let's introduce another form of the line, the equation of the line, that is. So far, the equation of the line has either been, pretty y equals mx plus b, where there's, the b here is 0, but also we had what? A standard form, where it's ax plus by equals c, or, maybe the x's and the y's are switched a little bit like they are here. But let's focus more on equations that are in the slope-intercept form, which looks like this. Let's change the color to this dark blue. Y equals mx plus b. there are two key elements here. Form. So m is the slope, which is rise over run, which is one thing we'll want to keep in mind in using the slope to go from the y-intercept, which is the b, to another point in order to graph the line. That'll be associated with the slope-intercept method. Okay, cool. So the y-intercept is b, but it comes to us as a form of a point 0, b. Okay, so keep that in mind, the point. Okay, now when your equation is in this form, y equals mx plus b, or in this case f of x, which kind of acts like a y, acts, not ask, lol, let's erase that, acts like y. You could just look at the coefficient of the x term in order to determine what the slope is. So we'll have slope, right, because we're trying to find the slope and the y-intercept for each one. So slope here is 2/3. And the b, which is the y-intercept, right, this is m, this is b. The b will just be the constant term that's tacked on. And if it's added, then the constant term is positive. And if it's subtracted, then I'm trying to erase that, then the constant term is negative. Okay, so here, again, we have the equation in the correct format, so we could just straight away pick the slope m of -4. Signage comes along for the ride, okay? Keep accidentally touching the screen when I don't want to. And then here your b is 5/3. That entire constant term, which could be a fraction, certainly. No problems there. Okay. So let's switch gears over to types of lines here. So horizontal lines always have a particular form to them, and so do vertical lines. Horizontal lines are always in the form of y equals some number. Let's go ahead and generically call it a, where a is just some real number, where vertical lines have the form of x equals a. And that's it. There's no extra stuff to it. Horizontal lines have no x term to them, just y equals some real number, and vertical lines don't have any y component to them at all. It's just x equals some, other real number. For horizontal lines, their slope is 0, okay? Vertical lines have undefined slope. And that'll become apparent once we talk more about the slope formula. We'll be able to calculate slope using a formula. And for when you use two ordered pairs that are on a vertical line, the denominator zeroes out, and so the value of the calculated slope becomes, by definition, undefined. So we'll see examples of that a little bit later on. So horizontal lines have a y-intercept at 0, a, and no x-intercept. Unless, of course, unless we have to make this caveat happen. You could be lying exactly on top of the x-axis, unless it's y equals 0, then the whole thing is, then the line intersects infinity times, intersects everywhere, we'll say. Okay. Then, if we are talking about a vertical line, right, and I'll come up with visuals here. In fact, let's go ahead and do that right now. A horizontal line, here's an example of one, right? It just looks like this. Pardon my squiggliness. And then the vertical line just looks like this, right? or some such thing. The vertical line, obviously, unless it's on top of the y-axis, is going to have no y-intercept, unless, right, same caveat, it's x equals 0, blah, blah, blah. We have the same kind of, yeah, explanation here as we do for this previous parenthetical bit. And the x-intercept will occur at a comma 0 right here. Okay, great. Let's sketch a graph of the following lines. Okay, so remember the structures, right? Any vertical lines are going to have the form x equals some number. Any horizontal lines are going to be y equals some number. So what's this? What type of line is this first one? It says x equals -6. Well, that's going to be a vertical line at -6. So that's 1, 2, 3, 4, 5, 6. That's all the way out here. It's vertical. So yeah, something like that will do. Here is x equals -6. Y equals 2 for number 2, right? So that'll be a horizontal line because it's y equals some number, and we're going to have it go through +2. So here we go. Something like that. All right, there's y equals 2. Now for this last one, we actually have a 6x6 grid here, positive and negative direction. So we'll have to make each, assume each tick is 2 units. So keeping that in mind, let's go ahead and do, what is it, horizontal or vertical line? Well, it's y equals some number, so it's going to be a horizontal line at -8. So let's say that this first tick mark is -2, -4, -6, -8. So it would be right there, like so. And that's all you really need to do. Like when you don't have enough space, you can just redefine what each tick mark's representative value is going to be. Just make a note of it, and that's enough for you to be able to graph it, even though at first glance it might seem like your coordinate plane is too small. And there you have it. So vertical lines are x equals some number, horizontal lines are y equals some number. Cool, that's everything for 7.1. Let's do one more section involving some more graphing, but we're also going to get into some word problem-y kind of things that have to do with rate of change, which is the more qualitative way to describe slope, which is a quantitative concept. Certainly, we're going to talk about slope in terms of a formula, right? So the rate of change of y with respect to x is given by the slope formula, which is, let me go ahead and put my drawer in play. M is still the variable associated with slope generally. And so you have change in, so this delta or triangle shape means change in y, change in x, which it could be rise over run. Like I'm just going to put all the different ways that we calculate slope. And that'll be, if you have two ordered pairs, one called x1, y1 or x2, y2, then you'll have the differences of the y's in the numerator. And then that's a subscript of 1. And the differences of the x in the same order in the denominator. Okay? So yeah, and it's just basically like, so it's given by this formula. So this is based on the idea of change in y divided by change in x. Okay, great. So let's find the rate of change for each description. So what we have here are a couple of word problems that describe a scenario in which basically two different scenarios are described, and it's our job to be able to take the information from both scenarios, which have two like intersecting bits of data, okay? And we should translate that into two ordered pairs and then use the formula right here, this M slope formula, in order to calculate the rate of change. Then we'll need to write a sentence describing the rate of change within the context of the problem. So here we go. Let's break it down. All right, here is number 1's example. I'll read it in its entirety, and then we'll start picking it apart to determine its rate of change. The number of worldwide subscribers of Netflix increased approximately steadily from 22.9 million users in 2011 to 62.3 million users in 2015. Find the approximate rate of change of the number of worldwide Netflix users. Okay, so we have two intersecting bits of data here. We have time and we have millions of users. And furthermore, for the time, what I would do to simplify things a little bit, so I don't have to use 2011, 2015, because those are large numbers, I'd rather just have T, and I'll have T be the acting like the X. So I guess maybe I'll just define it as X is going to be the number of years since 2000. And this is standard. You want to take a nice round number in order to represent the number of years that you've got. Like, so 2000 is a good place to start. So that means my X value for my first ordered pair will be what, 11, because that's how many years past 2000 to the year 2011 is. And then my other ordered pair will have a 15. Much easier to deal with 11 and 15 rather than 2011 and 2015, in my opinion. Y is going to be basically the resulting value. Okay, so we have, depending on the year, the millions of users changed. And notice that the units here are in millions of users. It's not 22,900,000. Like, I don't have that number all like expanded out. I'm thinking about these things in terms of millions of users. So I'm going to let Y be millions of users. So then it behooves me to define x1, y1, and x2, y2. So then I can feed it into my slope formula. So think of it this way. What are the combinations of years since 2000 and millions of users associated with the initial value in the scenario? Well, what came first? Well, there was 2011. Some data was taken on the number of millions of users. So the ordered pair associated with the 22.9 million users in 2011 would be 11, comma, 22.9. So what this ordered pair is representing is in 2011, there were 22.9 million users on Netflix. Let's do the same thing for the second scenario, the 2015 scenario. So it'll be 15 in the X position and then 62.3 in the Y position. So X2, Y2, the second ordered pair, is representing the scenario that in 2011, there were 62.3 million users on Netflix. Now let's go ahead and use the slope formula in order to calculate the rate of change. So you'll go 62.3 minus, because that's your y2, minus y1, which is 22.9. Again, just to be clear, I haven't rewritten the formula, but I'm using this formula right here. I'm going to actually circle it in yellow just for funsies. That's what I'm using. Okay. Just to be clear. Okay, where was I? So I have this difference of the y's in the numerator, and in the same order, I have to go 15 minus 11 in the denominator. If I go 11 minus 15 in the denominator, that's the reverse order of the scenarios concerning numerator and denominator values, and that's going to screw up your calculation in ways that you just don't even want to bother with. All right, so 62.3 minus 22.9 equals 39.4 in the numerator. And 15 minus 11 is 4. So it's not going to divide evenly, but let's just take out our calculators and go ahead and reduce. or simplify 39.4 divided by 4, and what do we get? Well, we get a nice round-ish value of 9.85. Now notice that the millions of users in the initial information were rounded to the nearest tenth of a million, right? There was only one decimal place, so we have 22.9 and then 62.3. Only one decimal place is presented here. So in order to uphold convention, I think it would be nice and appropriate to round this number to the nearest tenth. So we'll go, yes, we have millions of users per year, right? That's our rate of change, but we want to round to the nearest tenth, so we're in line with the decimal place values that were presented in the given information. This is standard, this is conventional, okay? So therefore, I'm ready to write my rate of change sentence, and I'll say the approximate rate of change is 9.9 million users per year. Okay. Also, furthermore, I want you to note one thing here, that the rate of change is positive. So that means, so rate of change means slope in the analogous graphical sense. Positive rate of change means an increasing line, an increasing graph here, okay? So we'll want to keep that in mind for future problems, just to be clear, okay? Let's do this same type of thing, but with a different scenario for number 2. And I'll change the color here to just for fun. Go this dark green. Here's number 2's prompt in its entirety. The number of postal employees declined approximately steadily from 583,908 employees in 2010 to 491,017 employees in 2013. Find the approximate rate of change of the number of postal employees. Now again, I'm going to go ahead and let the x be defined as the number of years past 2000. I think that's appropriate here for the same exact reasons as was mentioned before. And then here, we're going to need to show the entire number of employees, because, you know, the values that are presented here in the data that's given to us are, you know, we have, we're not rounding to the nearest like 100,000 or anything like that. We have the exact number of employees to deal with here. So it's more appropriate to have the entire number. So here for Y, we'll say number of employees. Okay, so let's take our 2 scenarios and label them x1, y1 and x2, y2 to get our ordered pairs, and then we'll feed them into the formula. So the first scenario mentioned was 583,908. So we're going to deal with a pretty big number here, but there's nothing we can do about it in order to truncate it and still maintain enough accuracy with our calculations. But here for the x value, we're just going to put a 10 because that represents 10 years past 2000, okay? With the second scenario, we're looking at the year 2013, and we had a decline in our number of employees to 491,017. There we go. So those are our ordered pairs. And so our slope calculation, or rate of change calculation, same thing, is going to be 491,017 minus 583,908. And then, sorry, the denominator will be 13 minus 10. So notice that the numerator value is going to be negative, and this is totally fine. We should expect that the overall slope is going to be negative because they used this word, right? We are representing, as far as the trajectory of employees over time, it should be declining, and so therefore the slope should be negative. So, but just to make the calculation finalized, I got 491,017, and I'm subtracting 583,908, and I'm going to get negative 92,891. And then 13 minus 10 is 3. Okay, so let's divide this number by 3, and we will get this number, negative 30,963.6 with a vinculum. Okay, so then that means that we are considering, with this hard calculation here, we're going to modify it ever so slightly to take into account the context of the problem, but we are finding that the calculation yields a fraction of 2/3 or 0.6s forever, right? So, but we're talking about people here with this rate of change. It's postal employees per year. How are they decreasing? So we're not going to talk about 2/3 of a person. That doesn't make any sense, even in terms of a rate of change. We need to round it to the nearest whole person. So we're going to bump this up by 1, basically, because this decimal value is 6, and any decimal, when you're rounding to the nearest whole and you have the next decimal place 5 or larger, then that means you're going to have to, right, check in with the neighbor. You're a 6, you're 5 or larger, so that means the 3 gets bumped up by 1. Okay, so therefore this will be approximately negative 30,964 people. So to get the rate of change sentence in play, we'll say the average rate of change and you can be super generic with the wording like I was in the previous problem too. The average rate of change is negative 30,964 postal employees per year. You must have units here. And again, like I alluded to earlier with the first problem, I want to highlight the fact that the rate of change is negative here, which means that the trajectory of postal employees as years move forward is getting less and less. The trajectory of that is falling, it's declining, it's getting fewer and fewer every year. So, you know, it's on a path to someday be none, unless, of course, the rate of change changes, which is certainly possible as well. It doesn't need to be lying on a strict line by any means. Okay? Cool. So, let's go ahead and review types of slopes. Now, in this next page here, I won't be able to show it to you all on one page unless I zoom out, which I'm going to choose not to. I just want to show you that there's 4 different types of lines and slopes and general graphs that we're going to encounter here. So in talking about rates of change that are positive, that is talking about an increasing line, okay? So that'll be here, we'll say the type of line in this first box will be increasing, okay? And the type of slope, it'll be positive. So we'll say m is greater than 0. Okay? And the general graph, you'll have a line that is going up, so to speak. It doesn't have to go through the origin. We just want it to have the ability to, as we scan from left to right, the trajectory of the line is going upwards. That's how you know it's increasing. And then you could certainly have decreasing, and that's when your slope is going to be negative, like with the postal employees. And there your m is going to be less than 0, and you're going to have your trajectory of your line go down. Okay? You certainly could have a horizontal line, which we talked about a second ago, which has a slope of m that is equal to 0, and that'll be like this, something like that. And lastly, we could have a vertical line, which has an undefined slope, and looks like this, parallel to the y-axis. Oh Lord, that was terrible. Let me try that one more time. Ah, erase it. Erase those silly lines. Okay, actually I have a straight edge with me that I'm using to help myself draw some of these lines so they don't look too gross and atrocious. There we go, that actually looks pretty good. There's a vertical line for you. Cool. All right. Great, so that's just some very, very surface elements associated with those 4 different types of lines. Now let's actually do some practice where we are using the slope formula, which I'll remind you is, if you have these 2 ordered pairs, which you already introduced in the first page, the slope formula is y2 minus y1 in the numerator, x2 minus x1 in the denominator. So go ahead and rewrite that formula down. You cannot write that formula down too many times. It's definitely, according to my own personal learning style, very conducive for memorization, or better yet, internalization of this information. So I recommend it. But if you learn in a different way, you have another way to make sure that you can recall this formula according to your own personal learning style, by all means do that. We have several different examples of practice here. So let's go ahead and do the right thing right off the bat, which is to assign who's x1, y1 and who's x2, y2. So I'm going to go ahead and say this one's x1, y1, the first ordered pair given, which is conventional, and then the second one is x2, y2. But you could switch them. In fact, for another example, I'll switch them just to, make sure that everybody understands that it doesn't matter, just so long as you are consistent with, once you make the assignments on who's x1, y1 and who's x2, y2, that you're consistent in the next step. That's all that really matters. So y2 here is going to be a 2 minus y1, which is also a 2. Hello. What's going to happen in this numerator? It's going to 0 out. But wait, let's go ahead and put the rest of the story together. -4 minus 1. So yeah, that's going to give you a 0 over, well, it doesn't really matter, -5, which is just a 0. Any line with a 0 slope is horizontal. Okay, so there's your horizontal example. Notice that we have 4 different types of lines and we have 4 different examples. Spoiler alert, you're going to see one of each. So that was the horizontal line. Let's, for fun, call this one x2, y2. The first one given, and the second one given x1, y1. Just so that you can see that it doesn't matter which one is which, just so long as once you make the assignment, you're consistent with your choice of that assignment. So y2 is -1, and then we subtract y1, which is a 9, okay? And then x2 is -7, and then we subtract x1, which is a -2. And whenever you're plugging in a negative number into any formula, be sure to put it inside of some parentheses just to be clear about the next appropriate step in regard to like sign changes, like so. Watch this, right? Boop, boop. We need to address that. Also, if you want to in the numerator, you can call this addition of the opposite. I don't know if that's more helpful or more confusing. You decide what's best for you, but that's ultimately what's happening. That's one way to think about it anyway. So here we have -10 in the numerator over 5, or excuse me, -5 rather. That's -7 plus 2. Which, boop, boop, those cancel out, and this settles down to a +2 is the slope. And since the slope is positive, right, this is going to be increasing. Okay, so number 2 is increasing, number 1 was horizontal. Okay, so we've got an increasing one. So we got 2 more to go. All right, here let's go back to, for no particular reason, x1, y1 assignments for the first item, x2, y2 for the second order pair. For, again, no reason at all. Just make your assignment, but then be consistent with who goes where. We're going to go y2 minus y1 in the numerator, x2 minus x1. Okay? Make sure you do any sign adjustments, like here, and maybe here too is an option, if you like that. And then we're going to go, that'll be -6 in the numerator, 4 in the denominator, and that'll settle down to -3/2, if I'm not mistaken. And just by virtue of being negative, we know that this line is decreasing. Okay, so cool. That's this one. So spoiler alert, the last one's going to be vertical line that goes through these 2 points. And you know how I know? Look at those x values. They're both the same. So that means the denominator is going to cancel out. But wait, hold on. Before I put anything into any formula here, let's decide who's x1, y1, who's x2, y2. I'm going to switch it up here just for funsies. Okay, and then the y2 will be 3, y1 is -5, x2 is -4 minus x1, which is also a -4. Let's do some appropriate sign changes. Boop, 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 boop. Yep, that's going to zero out. And it doesn't matter what the numerator is, but let's go ahead and just finish the calculation anyway. That'll be what, 8/0, but wait, that's undefined. And lines with undefined slope are vertical. Okay, so those are my conclusions. Let me go ahead and box them up in this other color, purple. Horizontal, increasing, decreasing, vertical. And then I have them all. I found them all. There's my vertical. Cool. Donezo. All right, so again, the moral of the story is trying to find what the slope of the line is between 2 points. You use the slope formula, of course, and if your slope is 0, you're dealing with a horizontal line. If your slope is undefined, you're dealing with a vertical line. If it's positive, the line's increasing. If it's negative, the line's decreasing. All right. Now let's take this into the realm of more word problem-y kind of things, right? Yep, that's what we're getting into here, if memory serves me, in the form of linear associations, which is just to say that if you have two different variables associated with like some data, and you find that the rate of change from one variable with respect to another is constant for all of your data, then you have a linear association, okay? So, and the linear association can be positive if the slope is positive, right? Or the rate of change. That's the key phrase that they're using here instead of slope, but they mean the same thing, especially in terms of calculation. And if the rate of change between two variables is negative, then that means the association will be negative, and the trajectories will be decreasing in that case, the trajectory associated with the data. All right, here's an example. Let me go ahead and read it to you, the first prompt to you in its entirety. It says, when a person begins a car trip, there are 12 gallons of gasoline in the car's tank. During the trip, the car consumes 2 gallons of gas per hour. Let G be the volume in gallons of gasoline after the person has driven T hours. Okay, they want us to identify the explanatory and response variables. So this hasn't been clearly defined yet, I don't think. Or wait, has it been? I think so. Yeah, it has. This has been ever given to you. So the explanatory is like the, it's kind of like I think about this in terms of a time frame. So this is the first element in the scenario, and this is the thing that comes next. kind of like cause and effect, kind of like actions and consequences. That's how I think of the explanatory and reverse or response variables respectively. There's something that happened first, and then there's another thing that followed from that, and that's going to be the response, okay? So first, if the two variables are g and t, it seems to me like you have to drive t hours, and then you'll be able to determine how much gas is left, right? What is the volume of gasoline after they have driven t hours? After they have driven t hours. So there's a time frame, keywords in here that are alluding to who is explanatory and who is response. So if it's after driving t hours, then the first thing that you did was you drove t hours. So t hours is the explanatory variable, whereas the response is the g, volume in gallons of gas. Okay, so let's construct a table to describe the association between t and g for the following values. So let's make a t-g table, kind of like our xy tables that we made earlier, and they're giving us specific values for t that they want us to use. So let's go 0, 1, 2, 3, 4, and 5. Make that a little bit longer. Okay, now let's figure out how many gallons of gas there should be, okay? With the scenario. So consider that the car hasn't been driven at all, okay? We're at the beginning of the car trip. It is said that there are 12 gallons of gasoline. So that should mean that if I've driven the car for 0 hours, I am at a full tank of 12 gallons. Well, whatever. Not necessarily like the full tank, but that's how many gallons of gas were read to be contained in the tank at the beginning. Okay, and if I am consuming 2 gallons per hour, so that's 2 gallons for every hour, 1 hour. This is the ratio, and I'm consuming, right? So that means I should be negative. I'm taking away 2 gallons every single hour. Then after the first hour, how many gallons should I have left? Well, I should take 2 gallons away for driving for 1 hour, right? So that means there's 10 gallons left. And then after 2 hours, I'll take 2 hours total. That's another hour away from the 10, or 2 hours away from the 12. However you slice it, it's going to be 8 gallons left over, right? Because you could take away 2 gallons for every hour that's driven. So take 2 more gallons away for the third hour. That's 6, right? And then take 2 more away. That'll be 4. And then 2 more. That'll be 2. Okay. So that means if I had driven a 6th hour, I would be out of gas completely, right? But they're not asking us to go for that duration there, okay? So now let's go ahead and graph the ordered pairs, and I'm going to do so because all of our inputs and outputs are positive. I'm going to go ahead and make my axes on the far left and bottom edges of the grid, okay? Like so. So here is my G axis, which is acting like Y. And here is my, my horizontal axis is for T, and it's acting like the X. Okay, let me just, so there's T. And I'm going to make the tick marks for T go like here's 1, here's 0. 2, 3, 4, and 5. And this is hours. Whereas I'm going to make every 2, so 2, 4, 6, 8, 10. That's not going to be enough, so I'll make it, this will be 2, that'll be 4, 6, 8, 10, 12. So I'll have some leftover, right? Some 14, that's fine, okay? This will be gallons of gas. Okay, and let's go ahead and plot our ordered pairs, and I'll do that in a different color just so that it shows up nicely against this purple. So we'll have 0, 12. So when time t is 0, I'm all the way up in the 12 right here, okay? And after 1 hour, I go down by 2 for a 10 right there. In 2 hours, I'm down to 8. 3 hours, I'm at the 6. And look at that, it's making a line, isn't it? Totally falling on a line, okay? And that's all it says to do, is to make the TG table and graph the ordered pairs. So I have done that, and I'm just going to leave it at that for now. For number 3, it asks, explain how this example suggests that if the rate of change is constant, then there is an exact linear association between the variables. Well, the rate of change is a constant. It's you're decreasing by 2 gallons for every hour, right? So certainly that's true. And check out the data that came about from using that bit of information. All of the ordered pairs lie clearly on a line, so therefore the association is like obviously linear. So let me go ahead and write a little blurb about that. The constant reduction of gas yielded data that lies on a line. Making the association linear. And then they want to know, is the association positive, negative, or neither? What does that mean for this situation? Well, the association is definitely negative because we determined that the rate of change was negative. We were taking away 2 gallons of gas for every hour that the car was driven. So the association is negative. And what does it mean? Well, in the context of the problem, it means we're going to run out of gas soon. Is negative, which means in this situation we will run out of gas eventually. All right, and that's all that I have for this lecture video. So again, because of the way that things are scheduled for this class, we will now spend the class period, of course, spending some time on these 2 sections, the concepts therein. But please do remember that this is the beginning part of Unit 4, and therefore it has no bearing on the material that you're expected to know for your upcoming Exam 3, which covers Unit 3 material. So make sure you are aware of that. Okay? Thank you so much for your attention, and I'll see you soon.